Today we're going to mostly talk about commitment schemes, and then I'm going to switch to the idea of secret sharing for making our random number generation that we saw in the previous session a little bit better. Whether it becomes better or not is really a matter of opinion. You'll see what I mean very soon. So let's just talk about commitment schemes for a second. So we already know what commitment schemes are. Basically, it's this idea that instead of revealing a value, you first reveal its hash, and then you wait for all the other players or all the other parties to the contract to do the same thing. And then after everyone has committed to their hashes, we open the hashes, we reveal the hashes and show the actual value that was hashed. And the basic idea is, of course, if you put a hash of something into the contract and everyone can see that you have committed to a particular hash, then it's impossible for you to change the original value, because changing the original value will also change the hash. Okay. But now I want you to see two different areas where we can use these commitment schemes, and I want you to really see the conceptual difference between the use of commitment schemes in these two problems. So the first problem we talked about was random number generation. Okay. So the idea here was that we have a bunch of different players and we want to generate one random number. So we ask each player to give us a number. So let's say player I gives us the number Ri. Okay. And of course, since we have a commitment scheme, what this actually means is that player I first commits to the hash of Ri and then waits for everyone else to commit. So this is done in the first phase. And then we have the other players all committing. And then in the second phase, player I actually reveals their number, Ri. And the idea here was very simple. Everyone can check that this revealed number has the right hash. So that's not too hard. This was our second phase. We can be sure that the players cannot cheat by changing their value of Ri, but the problem we had here was what happens if a particular player does not reveal the Ri. So specifically, we wanted our final result, our random number R, to just be the XOR of all the Ris. So if I use this to show XOR, I want the XOR of I from 1 to n of Ri as my output random number. Now, I just want you to see what kind of problem we have here. The idea here is that every player wants to keep their random number Ri hidden. And our problem is what happens if some of the players choose to never reveal it. So if I want to be very specific here, it is in an honest player's best interest not to reveal their value, at least in the first phase. Okay. And then our problem is, what if someone decides not to reveal in the second phase? Okay. What if a malicious player does not reveal in the second phase? And actually, I want you to see that the situation here is very similar to some of the other problems that we have seen. So let's see. We've already seen the problem of playing a game. So for example, let's say rock, paper, scissors, right? That's our toy example that we use for everything. If Alice and Bob want to play rock, paper, scissors, again, I have a situation that is very similar. They have to choose some strategy. So let's say Alice and Bob choose some strategy. I'm going to show this with RI2 just to have the same notation as that one. And this RI is going to be either rock or paper or scissors. And then we somehow compute based on the values of RI who has won the rock, paper, scissors game. Okay. But again, if you look at it in the first phase, where they announce the hash, so they each announce the hash of their value. This is our phase one. In this phase, actually, none of the players wants the other player to know their hash, right? So the only real problem we have is that in the second phase, they might not want to reveal. So in the second phase, they reveal the value of RI. And it's very similar to the case of RNG. So here the problem I have is, suppose I'm Alice and I'm playing rock. So I've announced the hash of rock. And of course, just assume that all of these hashes also have a nonce in them. I don't want to talk about nonces. So I've announced the hash of rock. And let's say that Bob announces some hash as well. And then when the first phase ends, Bob reveals, and I see that Bob has played paper. So I know that I've lost. So now I have an incentive to decide not to reveal in the second phase. Okay, so the situation is very similar to the random number generator. So we talked about this last session. Suppose that we're doing a lottery and I'm one of the players. Maybe I've bought a lot of the tickets. Maybe I've bought half of all the tickets. And I commit some hashes. And then when the first phase ends and in the second phase, everyone is revealing, I realize that, oh, if I reveal all of my hashes, I'm going to lose. So I decide not to reveal some of my hashes, or I decide not to reveal one of my hashes. Okay, so in both of these cases, as you see, we have a situation like this. In phase one, everyone wants to really keep their values secret. We're sure that no one wants to leak their values in phase one. The problem is really in phase two. The problem is in forcing them to reveal their values in the second phase. Okay. And now another example of this that we have also seen is again the case of auction. So this was in your homeworks, you had to implement an auction. Again, there we had a very similar situation. Every player I chooses some bid, which is the amount that they're willing to pay for the item. And then exact same thing. So they announce the hash of their bid. And again, of course, we should use nonces whenever we're doing the hashing, but I'm not writing the nonce here. And then in the next step, they reveal the values. Okay, just as before, let me write first phase here and second phase here. So as you see, here we again have a very similar situation. None of the players wants the other players to know their value in the first phase. So I don't have to really be worried about leaky players in the first phase. There is no benefit in letting other people know your bid. But again, the problem is, suppose everyone is revealing their bids and you realize that you have overbid by a huge factor. So maybe you've bid, let's say, 1,000 Hong Kong dollars, and everyone else was bidding $10. Okay, then you might choose not to reveal your value. So that's another problem. But all three of these protocols have basically the same situation, where the problem is that a malicious person might choose not to reveal their value. And for all of them, we can have the same solution, and the solution is to just have a huge deposit. Okay, so I can say that in the first phase, when player I commits to the hash of Ri, they have to also pay a huge deposit and pay a deposit D. Okay, and then if in the second phase they don't reveal, then we would just confiscate their deposits. Okay, so here I would say player I's deposit is burned if Ri is not revealed. Okay. Now, this works as long as your deposit is large enough, right? And let's see actually what's really large enough here. So let's actually start with rock, paper, scissors. Suppose that they're playing over 1 ether. So then if they want to cheat, they can win at most 1 ether, right? So if you put a deposit of, let's say, 2 ether, that's enough. You can be sure that they have no incentive to cheat. They will always reveal, because even if you reveal and you lose the game, you're still losing less money than the case when you don't reveal and you lose your deposit, because the deposit is larger than the amount that is at stake. I can do something similar for the auction. I can just say that whatever you deposit has to be larger than your bid. Of course, enforcing this is a little bit harder, because when you're bidding in an auction, your bid is supposed to be private, so no one else should see your bid. But at the same time, you have to also put a deposit. So here I say that player I chooses a bid Ri and puts a deposit which has to be at least D units. Okay. Now, here, again, the value of D should be so large that it exceeds anything that player I would possibly bid. Because I want to make sure that not revealing their bid is going to be costlier than actually revealing their bid and losing in the game, or losing in the auction, or in this case, winning the auction and having to overpay. Right? So one technique I can use here is that I can say, okay, I don't know what your bid is, so I'll just let you deposit any amount that you want. But if the amount that you've deposited is less than your bid when you reveal your bid, I'm going to just say that this is cheating and I'm going to confiscate your deposit. Okay. So that makes sure that no one would deposit less than their bid, because what's the point of doing that? Because if you deposit less than your bid and you don't reveal, you just lose your deposit. And if you deposit less than your bid and you do reveal, you again lose your deposit. So this is a way of ensuring that everyone puts a deposit that is large enough. Okay, so we can do this in rock, paper, scissors. We can do this in auction. So again, announcing HRI and putting deposit. So the deposits are always put in the first phase. But for random number generation, and especially for the case of lottery, this is not that great, right? Because imagine that you have a lottery with maybe 1 million participants. And let's say that someone has bought half of all the tickets. So for that person, since he has half of all the tickets, it makes sense not to reveal one of the tickets if he's not winning the entire lottery, right? Because even if you restart the lottery and do it again, then the malicious person has 50% chance of winning in the next lottery. So if I'm a malicious player who holds half of all the lottery tickets and I see that I'm not winning right now, it makes sense for me to just lose one deposit. Maybe I even own more than half of all the tickets. Maybe I own 90% of all the tickets. And if I see that I'm not winning, I just decide that I'm going to take one of my tickets and not reveal it. Okay. And of course, if I don't reveal it, then I'm affecting this entire result R, and that cannot be allowed, because if I can tamper with R, then I can make it so that I win, and we don't want to allow that. So the only way is to restart the entire lottery and the entire random number generation. But if we do that, again, if I have 80% of all the tickets, I will have an 80% chance of winning in the next round, even though I didn't win in this round. So this deposit here has to be so large that not revealing even one ticket's RI is going to cost me an enormous amount of money, more than anything that I can possibly win in the entirety of this lottery. So in this case, the challenge I have is that D, the deposit D, must be larger than all the money in the lottery. It has to be larger than the sum of the values of all the tickets. Okay, which is just an astonishingly large deposit, because if you think about it, let's say I have again 1 million people taking part in my lottery, and each one of them is buying a ticket that is worth $1. Now I'm also asking each of them to put a deposit of $1 million, right? So this idea of putting a deposit doesn't really work for random number generation. I mean, it works, but it only works if your deposits are insanely high. But in these two other cases, your deposits actually don't have to be insanely high. But now I want to show you another problem, and this problem is actually going to be conceptually different from these three. And this is the problem of escrow. So we talked about this before. We said that suppose Alice and Bob want to buy and sell some physical good that is not on the blockchain. So Alice is the buyer and Bob is the seller, right? And we talked about this before. We said that Alice puts a deposit first, maybe Bob also puts a deposit, and then Bob has some time to send the item in the real world to Alice. Okay. And then afterwards, after the deadline for Bob to send the item to Alice passes, each one of the two players has to say whether they've received the item, whether they think the item has been fulfilled or not. Okay. So this is our situation here. Every player, player I, has to announce one value. And this was actually just one bit, RI, which is basically just going to say whether the item was fulfilled or not. Okay. Now, we've talked about this before, and we've talked actually about the fact that Bob can try to extort Alice. And also the other way around. Alice can also try to extort Bob, and we've seen how a successful extortion attack can work. So now a question here is, why can't we just use commitment schemes to solve this? Right? Because it seems like if you just look at it naively, it seems like the problem we had when Bob could extort Alice was that they weren't really moving at the same time. They weren't really announcing their values at the same time. So Bob could just announce some dishonest value, and then that would be used to extort Alice. More specifically, maybe Bob didn't send the item, but then he just sent a message on the blockchain announcing that he has fulfilled the item. And now because Alice can see the blockchain, Alice can see that Bob is lying. And then the way that the escrow protocol was designed, Alice either has to agree with Bob's lie and gets part of her deposit back, or she has to say that, no, I don't agree with Bob's lie, and then all of the money will be burnt. Okay. And of course, if Alice is rational, if Alice wants to maximize her own earnings, her own payoff, she would just accept the extortion. We can have a lot of discussion about what happens in the real world, because basically the situation here is like this. Let's say that Alice has put a deposit of 2 units and Bob has put a deposit of 1 unit, right? And Bob hasn't sent the item to Alice, but he has announced on the blockchain that he has sent the item to Alice. Now, what are Alice's choices? Alice's choices are to either accept the extortion or not. So if she accepts the extortion, actually, let me just write the numbers with different colors. So if she accepts the extortion, she's going to get 1 unit back, and Bob is going to get paid 2 units. But if Alice does not accept the extortion, then she's going to get no money back, and Bob is also going to get no money back. So these are Alice's 2 choices. Either she gets paid 1 unit and Bob gets 2 units, or no one gets anything. Now, if this happens, if Alice is rational, rational means that she's only worried about her own payoff and she just wants to maximize her own payoff. And she sees that she's making 1 unit here and nothing here, so she would prefer this choice and she would accept the extortion. But in the real world, most people are not rational. If you see that someone else wants to extort you, it's actually likely that you would choose this option. You would say, okay, I'm going to lose 1 unit, but I'm going to make them suffer as well. Okay, so that's why this kind of escrow might actually work in the real world. But this is no longer computer science or economics, it's just psychology. Okay, but if we want to look at it completely from a computer science and game theory point of view, Alice will have no choice here but to accept the extortion if Alice is rational. Okay. Now, what was the root of this extortion? The root was that Bob could announce his choice, his value Ri, sooner than Alice. And if you look at all of these previous problems that we've solved, so RNG, rock, paper, scissors, and auction, here we had a similar issue. We had an issue that some players might submit their values sooner than others, and then those people who submit their values later can see the values of the previous players and they can basically cheat. So especially if you look at rock, paper, scissors, if I didn't have the commitment scheme in place, then when Alice announced her value, Bob could see her value on the blockchain, and then he could choose his value so that he always wins the game. So the entire idea of using a commitment scheme was to somehow simulate simultaneous behavior, right? So I want both Alice and Bob to play at the same time. And that's why I cannot make them actually play at the same time. So I just use this 2-step commit and reveal process to kind of simulate simultaneous action. And it's the same here. So I want everyone to bid at the same time. I cannot really force them to do that on the blockchain because that's just the way the blockchain system works. So instead, I simulate it. I make it so that the protocol works as if they're working simultaneously, as if they're sending their bids simultaneously. And the same thing here again. So the entire role of a commitment scheme is again to simulate simultaneous action by the players or parties to the contracts. So now the question is, can I do the same thing in an escrow? Can I have an escrow where I say, okay, Alice and Bob, you're not supposed to just announce your value RI, which says whether it was fulfilled or not, but you're supposed to use a commitment scheme. So let's see what happens here. Let's use a commitment scheme. So here, the difference is that, again, I will have two phases. And in phase one, each player, so player I, who's either Alice or Bob, announces the hash of their choice to the contract, hash of RI. And let me actually put the nonce here as well. Hash of their choice and their nonce to the contract. And then the second phase is that each player reveals their choice and their nonce. So player I reveals both their choice and their nonce. Okay. Does this stop the extortion? Because it now feels like they're moving at the same time. So it feels like there's no way for Alice to know what Bob was doing. So even if Bob is being dishonest, since Alice doesn't know that Bob is being dishonest, Alice would play honestly, and then they would both lose all of their money. So there is no incentive for Bob to be dishonest, right? So if you look at it from Bob's point of view, it seems like assuming that Alice is going to play honestly, you have to play honestly too. Otherwise, you will lose a lot of money. But that's not actually the case. So can you see the attack here? Can someone maybe give me an attack in the chat? So there's something conceptually different about this escrow and these previous examples that we saw, RNG, RPS, and auction. What's conceptually different here? Any ideas? So you see the conceptual difference is in the incentives. In all of these examples, each player had an incentive to keep their value hidden in the first phase. So in the random number generation, for example, you didn't want other players to know what RI you're playing when you're in the first phase. In RPS, of course, you don't want the other player to know what you're playing in the first phase, because then they would just play the best strategy against you and they will win. In the auctions, it's a similar situation. You don't want other people to know how much you're bidding, because they can just bid higher than you, right? So in all of these cases, it was in every player's best interest to hide their input, to hide their strategy, bid, whatever you want to call it, to hide their RI in the first phase. And then the only problem we had was, what if they also keep it hidden in the second phase, and then we solve that with a deposit. But we didn't have a problem where a player wanted to intentionally leak their value in the first phase. But here we have that problem. So here, actually, if Bob wants to extort Alice, Bob wants to intentionally leak his value. He wants Alice to know that he's saying the item was fulfilled, even though it wasn't, because that's the whole point. That's the whole concept of the extortion. Bob wants Alice to do this kind of analysis and say, I'm either going to get 1 unit back and give 2 units to Bob, or I'm going to get nothing back. And in order for Alice to be in that situation, in order for Alice to be extorted, Bob needs to actually show to Alice that he's playing this particular RI, that he's saying the item was fulfilled. So actually, the attack here is very simple. The attack is that Bob says the item was fulfilled. So let's say that fulfilled is shown with 1 and not fulfilled with 0. So Bob sets RI to 1 and leaks the value to Alice, and leaks RI to Alice. And this is done in phase 1. So Bob intentionally goes out of his way to make sure that Alice knows what he's playing, that Alice knows that he's playing RI equal to 1 and knows his nonce. And of course, Alice can verify this. So if I'm Bob and I send you the nonce and I say, hey, I'm playing RI equals to 1, you can of course see my message on the blockchain. You can see that I've committed to this particular hash in the contract. And then you can just check that the hash of RI and the nonce that I'm claiming to you is the hash that I've put on the contract. So you can be sure that I'm not lying, I'm not bluffing. I'm really saying that, well, I am lying to the contract, but I'm not bluffing about my lying. I've really said to the contract that RI is equal to 1. And then if you're Alice and you're in this situation, again, you would be extorted. So a commitment scheme doesn't really work in this case. So commitment scheme can model simultaneous action only if the players don't want to leak their actions. If the players want to intentionally leak their actions, commitment schemes are useless. Okay. So in this case, a commitment scheme is useless. And that's why when we were talking about this escrow contract, I didn't really bring up an escrow with commitments. Okay. I really hope that you understood this part. If you didn't understand it, please ask me any questions you might have. This is definitely going to be on the final exam. Okay. But let's go back to our random number generation now. So let's go back to RNG. Now, the problem we had here was not really a problem with commitment schemes. It was a problem with the amount of deposits that we have to put, right? So the commitment scheme here works because, again, the important property that we need to have for commitment schemes to work is that we want every honest player to be incentivized not to leak their value in the first phase. And here, every player really has an incentive not to leak their value, because what's the point of leaking your value to others? You're just giving more information to them. You're putting them at an advantage in comparison to yourself. But the problem, of course, is that this deposit is too large. And the whole reason that we are putting down this large deposit is because we want to be able to force the player to reveal their value. Okay. So the flaw in our system is that the players can choose not to reveal. Okay. So this is the main flaw. A player can choose not to reveal. And we saw how this can create all sorts of problems for us. Okay. So what is the solution? Well, the simplest solution that comes to mind is to design a protocol where the players have no choice. Design a protocol where even if one player does not reveal their value Ri, it gets revealed anyway. Okay, so this is what we want to do today. Design a protocol in which Ri is revealed even if player I doesn't want to reveal it. So if we can design a protocol like this, then we've solved the main problem here, which was that I might have a player who doesn't reveal, and that player not revealing actually affects the final result. If everything is going to be revealed anyway, if as a player you cannot stop your value from being revealed, then there's no point in all of this, right? So it will be revealed, and that means that the correct value of R, which is the XOR of all the RIs, or well, the sum of all the RIs modulo some other number, depends on your implementation, the correct value of R will be computed anyway. So this really gives us a tamper-proof property that no one can avoid revealing their value. Okay, but how can we do this? Well, today we're going to see one way of doing this, and in the next session, we're going to see another way. So today's way of doing this is called secret sharing. And to present this, I'm going to actually first give you a completely different problem, and then I'll show you how it can be used in the random number generation. Okay, so secret sharing is this. Suppose that you hold a secret, or suppose, let's give it a name. Let's say Alice holds a secret. And let's call this secret S. Okay. And as usual, let's say that this secret S is a number. And let's say that it's a number modulo P. Okay, so it's in 0, 1 to P minus 1. Okay. And here, let's say that P is again a large prime number. So another way of writing this is that Alice holds a secret S. And my first step, let me write it a little bit further down. My first step is that Alice chooses a large prime number. P, which is greater than S. Okay. Again, this is just standard, like the case of RSA and all the other previous things that we've seen. We want to have a way of saving our secret messages, or our secret S in this case, as a number. And then we want to be able to do calculations modulo some other number. And I just want to do calculations modulo P. Okay. But what are my goals? So let's get back to the problem and actually define the problem. Suppose that Alice holds a secret S, and let's say that she has n friends. Okay. And she has n friends. Let's call them, I don't know, F1, F2 to Fn. Now, here's the goal. I want to give each one of my friends a share of my secrets. Okay? And I want to make sure that if enough of my friends come together, they can reconstruct the secret, but otherwise they can't. Okay? So actually, maybe let me use the entirety of this line. So I'm going to say Alice holds a secret S and she has n friends. She wants to give every friend, let's say Fi, some number, a number Si. And this is going to be called a share. Okay. Now, what are the properties that I want to have? I want to have these two properties such that, one, I want to say that if T of my friends come together, they have to be able to find the secret. So any T of the friends can find S, the original secret. And the second property I want to have is that if fewer than T of my friends come together, they shouldn't be able to find any information about my secrets. So any T minus 1 friends can find no information about S. Okay. Yeah, so basically the idea is that, well, if you set T to be, for example, half of your friends, you can say that if a majority of the people wants to open the secret and figure out what my original secret S was, they should be able to do it. But if less than a majority of the people want to open it, they shouldn't be. So I'm going to have a threshold T. This is my threshold. And I'm going to say that if T of my friends come together, they should be able to compute my secret S. But if the number of friends that come together is less than T, even if it's T minus 1 of my friends, they should find no information about S at all. Okay? So again, ask any questions you might have in the chat if this is not clear. So how do I do this? Well, the idea is actually to use polynomials. So I'm going to choose a very large prime number P that is larger than S, and I'm going to say that all of my calculations are modulo P. Okay, so all calculations are modulo P. And let's say that I also announce P to everyone. Okay, so Alice announces P to every friend. Okay. Now, here's the part where things get interesting. Let's remember some algebra. So I'm going to do an algebra refresher. Let's say that I have some function, and let's say it's a polynomial. So I've already used F for friends, and I've used P for the prime number. So okay, let's say G is a polynomial of degree D. Okay. If I have a polynomial of degree D, and if I want to give you this polynomial, well, one way is to just write this G, and I say, for example, G of X is something like this. It's A0 plus A1X plus A2X squared, so on, to ADXT, right? So if I want to send you this polynomial g, one way of encoding g, one encoding of g would be to just give you all of these coefficients. So I can give you a0, a1, a2 to ad. If I send you this message, then you can, of course, reconstruct the polynomial g. Okay. But another way of encoding g is to just give you a bunch of points that this polynomial goes through. Okay. So maybe I can give you a bunch of points. Let's call them x1, y1, x2, y2, and so on. And x, okay, let's say I'm giving you k points, xk, yk. And then I just tell you that these are points that this polynomial passes through. So I can tell you that when I'm giving you this point, what I actually mean is that I'm telling you that g of x1 is y1, and g of x2 is y2, and so on. And g of xk is yk. So how many points should I give you so that you can reconstruct the polynomial g? D plus 1, right, yes. So if you have d plus 1 points, you can definitely reconstruct the polynomial g. And to see this, let's just do some really silly and small examples here. First of all, if g is just a constant, if g of x is of degree 0, if it's just a0, then I just need to give you 1 point, right? Because if I give you x1, y1, then you are sure that y1 is equal to a0. If g of x is a0 plus a1x, then g of x is a line. And of course, a line is uniquely determined by 2 points. So a line is uniquely determined by 2 points. And so on. And generally, a polynomial of degree d is uniquely determined by d plus 1 points. So if I give you d plus 1 points of this polynomial, you can compute it. Okay. Now, why is this? Well, you've probably seen a proof of this if you've taken a course on linear algebra or on basic algebra, abstract algebra. If I want a polynomial that goes through all of these points, x1, y1, x2, y2 to xk, yk, how can I create that? So let's say that I first create a polynomial gi, first create a polynomial gi such that gi of xi is 1 and gi of xj is 0 for every j that is not equal to I. For every j that is not. Okay, so let's say first I create a polynomial like this. Now, how can I create a polynomial like this? And I can do this for every j that is not equal to I. So if I just do this thing, so if I define the polynomial gi of x to be the multiplication for every j that is not equal to I of x minus xj over xi minus xj. Okay, So first of all, none of these denominators are 0 because I'm just doing xi minus xj when j is not equal to I. Now, if my x is one of the xj's, then at some point I have xj minus xj here in the numerator. So the gi of xj actually is 0. But then the gi of xi is 1, because if I take gi of xi, it's just xi minus xj all over. So I'm just multiplying a bunch of ones. So now I have the desired property, right? So if I create my gi using this simple formula, then I'm sure that it's a polynomial that is equal to 1 at position xi, and it's equal to 0 at every other xj. Now I can, that's not what I wanted, right? I wanted a polynomial that was equal to y1 at x1, equal to y2 at x2, and so on. But now I can make that polynomial using these building blocks. So I can just say that I compute g of x to be what? So I just take y1 times g1 of x plus y2 times g2 of x, and so on to yk gk of x. Okay, so g1 of x had a value of 1 at x1 and 0 everywhere else. So y1 times g1 of x has a value of y1 at x1 and 0 at every other xi. And then the same thing here. So when I sum these things up, I can be sure that g of x1 is y1, g of x2 is y2, so on, and g of xk is yk. Now, but what is the actual degree of these things? So if I have k points, what is the degree of this gi? The degree of this gi, let me actually write it. The degree of gi is actually k plus 1. Sorry, k minus 1. Because I'm multiplying k minus 1 different terms here, different k minus 1 different monomials. So the degree of gi is k minus 1. So in other words, if I want to encode a polynomial of degree d, I need to have d plus 1 points. And if I have d plus 1 points, if I'm given any d plus 1 points, I can find the unique polynomial of degree d that goes through those d plus 1 points. Okay? Now, the nice point here is that these polynomials don't have to be over real numbers. So this x here doesn't necessarily have to be a real number for our argument here to work. This x can actually come from any field. So for our use cases, the thing that is important is that this x can be a number between 1 and p minus 1. It can be a number modulo p. Okay, why is that? Why is it enough to just have a number modulo p? Intuitively thinking about this, you just want to be able to divide, and you want to be able to multiply, of course. And you can do division when you're doing calculations modulo p because we have modular multiplicative inverse. Or another way of talking about this is that we have a field of numbers modulo p. So since it's a field, everything here works out. Okay. So let's go back here. So I have a secret S. I want to give it to n of my friends. And I want to give each one of my friends one number Si. And I want to do this so that any t of my friends can find my secret, but any t minus 1 of my friends cannot find any information about my secret. So this reminds me of this part, right? So if my secret, instead of just being a number, if my secret was a polynomial of degree d, then given any d plus 1 points of it, I could find the polynomial. But if I were given only d points of it, I could not find the polynomial. So this is what I'm going to do here. So I want to say that any t of my friends can find S. So the step 2 of the protocol is that Alice creates a polynomial of degree. Okay, what should the degree of my polynomial be? Tell me the degree in the chat. Really? Not that obvious? Okay. So Alice creates a polynomial g of degree t minus 1. Okay. And the idea here is that g of x is a0 plus a1x plus a2x squared, so on, to at minus 1 x to the power of t minus 1. Now, I want to give shares to my friends. The shares that I'm going to give to the friends are just going to be points in this polynomial, points that this polynomial goes through. Okay? But I have to also somehow encode my secret in this polynomial. So let's encode my secret as one of the coefficients of the polynomial. Okay? So let's say I create a polynomial g of degree t minus 1. I set g of x like this. And I say that I want a0, which is basically g of 0, to be my secret. So I set this a0 to be my secret s. And then I choose all of the other coefficients randomly. Okay? Choose. Let's write it here. a1, a2 to at minus 1 are chosen randomly. Okay. So now I have to give shares. This is the third part. Alice computes the share, Si, and this is just going to be g of I, and gives it to the i's friend. Okay. So now each one of my friends, if they're my ith friend, they know the value of g at x equals to I. So Si is g of I. So now if t of my friends come together, they know t different values of g. And since they know t different points where g goes through, they can actually compute g. And when they compute g, they can just evaluate it at point 0. They can find g of 0. And that's my secret. Okay? So this is the sharing part. Now we have the reconstruction part. If I have t friends, any t friends, let's say fi1, fi2 to fit, can come together. And what do they have? And they have the value of this particular polynomial g at all of these points. They know g of I1, g of I2, all the way to g of ik. Okay, and since they know the g value at, g of it. Since now they know the g value at t different points, And since G was a polynomial of degree T minus 1, then they can reconstruct G using this Lagrangian interpolation that we had here. Okay, so sorry, someone's knocking on my door. Just a second. I'll be back. Okay, I'm sorry. Someone was here to fix the air conditioning of my office. Okay, so any T of my friends can come together and they know the value of this function G at T different points. And so they can just apply the Lagrangian interpolation, especially since G was of degree T minus 1, and they can find G, they can evaluate it at point 0, and that gives A0. Okay, so they have GI1 to GIT, they can reconstruct G by Lagrangian interpolation, and then compute G0. And G0 was, of course, my secret S. So T of my friends can come together, they can find my secrets. Now let's see what happens if T minus 1 of my friends come together. Because remember, I wanted to have two properties. I wanted to make sure that any T of my friends can find my secret. And I also wanted to make sure that if fewer than T friends come together, they can find no information at all about the secret. Okay? So to have the second property, let's say T minus 1 friends come together. So consider T minus 1 friends. And let's say again, this is Fi1, Fi2 to Fit minus 1. What do they know? They know the value of the function G, the value of the polynomial G at T minus 1 points. So they know G of I1, G of I2 to G of It minus 1. So they know G at T minus 1 points. And none of these points are point 0, right? So I know that 0 is not in the set I1, I2 to It minus 1. Because my friends were numbered from 1 to n, and friend I got G of I. No one got G of 0. So I'm pretty sure that they don't know G of 0. Now, here's the part where I say they can find no information. So I can take the information that they have, and I can put any value for G of 0, and that would still be a valid polynomial of degree T minus 1, right? So for any arbitrary value, let's give it a name. I don't know, let's call it U. There is a polynomial let's call it G of U that has these properties such that G of 0 is U, G of I1 is basically whatever we knew for I1, G of I2 is whatever we knew for I2, and so on. So such that G of 0 is U, and GU of 0 is U, and GU conforms to the knowledge of my T-1 friends. Okay, so what's the idea here? The idea is that they know T-1 points of this polynomial. But a polynomial is uniquely determined by T points, not by T-1 points, because remember, this polynomial is of degree T-1. So you need T points to know what the polynomial is. If you only know T-1 points of the polynomial, the value of polynomial at 0 can be any value. And for any value that I give you at 0, there is a unique polynomial that goes through that value at 0, and then goes through g of I1 at I1, g of I2 at I2, and so on. So this means that if T-1 friends come together, they can find no information about g of 0. G of 0 can be anything. And remember, g of 0 was my secret. So they don't know any information about my secret. So I have the desired property. My desired property was that any T-1 friends can find no information about my secret S, and that holds. Of course, they can only know that my secret is less than P, but that's something that I chose to tell them myself. So I just told them P and told them that all the calculations are modulo P. So my secret is also modulo P, it can be atmosphere. Okay. So now I have a very nice situation where I can use secret sharing, and I can make sure that any T of my friends can open the secret, but any T-1 of my friends cannot find any information about my secret. Okay, but we went this deep so that we can come back and solve random number generation. So what was our situation in random number generation? We were saying that every one of the players chooses a random number Ri, and then we say that our final random number is just the XOR of all the Ri's, or the sum of all the Ri's modulo some number n, right? And then our problem going up here was what happens if someone does not actually reveal their value Ri. And we wanted to say that if they don't reveal it, then other people can compute Ri. So now I can have a situation like this. I can say, okay, when you choose your Ri, you have to also give shares of your value to other players. And if you don't reveal in the end, the other players are going to put together these shares and they're going to reconstruct your value Ri. So this Ri, which was supposed to be used in the random number generation, is the secret S that you're sharing with everyone else. And this is the way that we can make sure you don't have a choice to decide whether you reveal or not. Even if you don't reveal, other people will reveal it for you. So now I have this protocol for RNG. So let's actually write the entire protocol. So let's say I want to have RNG by secret sharing. Okay. So these are the steps. I say in step 1, people have to sign up for the secret sharing, for the random number generation. So I will have some amount of time in my smart contract when people can come in and sign up. So players sign up with the smart contract, and let's say they also pay a deposit. Let's just call it D. Okay. And let's just assume that n people have signed up. So assume n people signed up. Okay. In step 2, every one of the players is going to choose some number Ri. So each player chooses Ri. And let's say that again, all of our calculations are modulo P. So maybe I have some big prime number P that everyone knows about. It's hard-coded in my contract. So I'm just assuming that everyone knows a large prime number P. Okay. So in the first step, the players sign up and they pay some deposit. Let's assume that n players signed up. Each player is going to choose an Ri. And again, these numbers are all modulo P, so it's at most P. And then each player is going to send each other player a share of Ri. So if player I chooses Ri, then player I also forms a polynomial Gi of degree t minus 1. We will talk about what t should be. Okay? And gives shares to every player j, to every other player that is not I. Okay? Now, step 3 is our normal commitment. Player I commits to the hash of their value and some nonce on the smart contract. And after everyone commits, everyone has to reveal. So step 4 is that player I reveals their values Ri and Ni. And now here, if a particular player does not reveal, then we will have another step. Step 5, if a player fails to reveal in step 4, then other players come together and reconstruct the value of Ri. Other players come together and compute Ri. And finally, the last step, step 6, is that our random value R, which is the output of the entire system, is just going to be the sum of all the Ri's, and of course, it's modulo P. So basically, what we're doing here is that we're saying you don't have the choice to not reveal. If you don't reveal, then the other players will get together, they will put their shares together, and they will figure out what your value of Ri was. So even if you decide not to reveal, your Ri will be revealed, and it will be added to this sum. So there is no way for you as a malicious player to actually change the final value of R. So we have tamper-proof random number generation. Okay, that's it for this session. In the next session, we're going to see actually a kind of a better way to generate tamper-proof random numbers. So you can leave now. I will stay and answer all the questions here. Okay, so one question in the chat is it possible that another player doesn't come together to reveal the secrets? Yes. So you see, I said we have to choose this value of t in a nice way. So here, in order to come together and reveal someone else's secret, you need at least t players. Okay, so here, at least t players are needed, right? So if I need at least T players here, then my assumption has to change. Previously, my assumption was that I have one honest player, and I was saying that even if one player is honest and honestly generates an Ri that comes from a uniform random distribution, then the entirety of R comes from a uniform random distribution. But now I need another level of honesty for this step. I need to have at least T players who are honest and who are willing to come together and put the shares together if a previous player, if some other player is dishonest and has not revealed in step 4. Okay, so that's the first thing. But then the other thing is, if you look here, any T of the players can come together, they can collude with each other, and they can compute all the Ri values of the other players. So if you have T dishonest players, these T dishonest players can basically unmask the values submitted by all the other players in the commit phase, in phase 1, before the reveal phase. So I should have 2 constraints at the same time. I need these 2 constraints. I need to have at least T honest players, because these are the players who are going to help me reveal the value if someone lied in step 4. And then the other constraint that I have is that I should have at most T-1 dishonest players. Because if I have T-1 dishonest players, these T-1 dishonest players can collude in step 2, and they can find the values of all the other players' Ri before they wanted to reveal, right? So putting these 2 together, it means that at least half of your players have to be honest. So our guarantee went from having just 1 honest player to a situation where we need at least half of the players to be honest. So our guarantee is very much like a Bitcoin guarantee now. So the guarantee is that R is tamper-proof. You cannot tamper with the final result R, as long as more than half of the players are honest. And actually, that's why I said you have to set the value of T in your contract. So in your contract, you have to first wait for people to sign up. You have to see how many people signed up. And then you have to set T to be half of the number of people who have signed up. Okay, another question in the chat is, what if a player distributes garbage shares? Good point. We can actually have a way of finding that out in step 5. So right now in my step 5, I'm saying that if a player fails to reveal, then the other players come together and compute Ri. But I can actually say that in step 5, we compute the Ri for every player no matter what, even if they have revealed in step 4. And then I can say that if we figure out that they've distributed garbage shares, which means that the shares don't really create a unique polynomial with the value with the secret value that they claimed, then we would just take their deposits, right? We can also have a rule that says that if you give garbage shares, your value will not be counted in this sum. Now, why is that okay? Why is it okay to say that if you give me garbage shares, then your value will not be added to this sum? Because when the player is deciding what shares to give, when we are at step 2, this player has no idea what the values, the secret values Ri of the other players are. So if someone decides to give garbage shares, they're deciding that at a time when they don't know anything about other players' strategies. So it doesn't matter. If they decide to give garbage shares, we can say that's as if they didn't give any shares at all. And then we don't add it here. They cannot really tamper with the randomness of R anyway, because they don't know about it. But again, this is assuming that we have these two constraints. So assuming that more than half of the players are honest, it's fine if people give garbage shares. Then we will just ignore the garbage shares, people who gave garbage shares, and we will take their deposit. And actually, just the threat of taking their deposit is enough to make sure that rational players will not do this. Because if you're a rational player, you know that if you want to give garbage shares, you have to do it at step 2. But at step 2, you don't know anything about the results. So giving garbage shares just means you lose your deposit without you actually being able to increase your chances of winning the lottery. So why would you do that?